Now let's go over the properties of the linear correlation coefficient r. The value of r is always between -1 and +1 inclusive. So another way we can write that is -1, r is greater than or equal to -1, less than or equal to +1, inclusive meaning it could be equal. So looking at that in a diagram form, we would have -1 here, +1 here, right in the middle is 0, where -1 represents a perfect negative linear relationship. So if we're exactly at -1, we have a perfect negative linear correlation or relationship. And at +1 is where we have a perfect positive linear correlation. Now, we will not run into r's that are exactly 1 or -1 because none of our data will come out to be perfectly positive or perfectly negative, but we need to have that understanding that the closer we get to 1, the closer we are getting to a positive perfect linear correlation or -1, and that's why earlier I talked about taking the absolute value of r and comparing that to 1, because r could be negative or positive, and as we compare that to +1, the closer the absolute value r is to 1, the stronger the linear correlation, whether it be negative or positive. So what's going on right here in the middle? Well, an r of 0 means there is no linear correlation. So we'll be running tests and getting test statistics, an r value that's somewhere on this scale, and we'll be determining whether or not that it's close enough to 1 or -1 to indicate a linear correlation, or if it's not, and we'll actually have critical values, and we'll have critical regions and our test statistic, and we'll compare those and make decisions about those just like we did with our hypothesis testing. It's just another form of hypothesis testing. Okay, let's look at the second property of the linear correlation coefficient r. If the values of either variable are converted to a different scale, the value of r does not change. So in other words, if I had heights in inches and I changed them to centimeters, it wouldn't change anything about whether or not there's a linear correlation between height, my example I had before of a plant, that height it had grown with compared with the value of the amount of sunlight it had received. So that's my paired data, the height of the plant and the amount of sunlight, and I could change my height, say, from inches to centimeters, but that won't change the value of r, or whether or not there's a positive correlation or a negative linear correlation. The third property of the linear correlation coefficient is that the value of r is not affected by the choice of x or y. So in this example I'm mentioning about the plants, we could say, is there a linear correlation between the amount of sunlight exposure, x, and the height, y, of the plant? Or I could say, is there a linear correlation between the height, x, of the plant and the amount of sunlight exposure, y? Now, of those two, the first one, where x is the sunlight and y is the height, x is the amount of sunlight exposure and y is the height, that's probably a better way to state this particular problem or experiment that you might do. But either way you state it, the value of r is the same. Okay, our fourth property is that R measures the strength of a linear relationship. I keep saying this, but I want to make that clear, that just because we determine maybe that there is no linear relationship, no linear correlation, that doesn't mean there is no correlation, because it may be a different type of relationship, a curvilinear relationship or something like that. And finally, R is very sensitive to outliers. We've mentioned this before. If we do have outliers that we know are the result of errors, we need to remove those. If we need to keep them in, we just need to be aware that R is going to be very sensitive to outliers in our data.